Hello everybody, and welcome to the beginning of section 5.4. We're looking at page 9 in the workbook, and the topic of this section is called integration by parts. Now, before we dive into this, I want to just say a word about kind of the course in general. These first few weeks of Calculus 2, the general goal is to sort of build our toolbox of integration a little bit bigger. In the last section, we talked about integration using U substitutions. That was the technique that you generally learn at the end of Calculus 1. And it turns out that there are a lot of other techniques that can be developed for calculating antiderivatives. Okay, so integration by parts is the next technique that's going to be in our toolbox here. Okay, and what's interesting about this particular technique is it can be derived from the product rule for differentiation. I want to show you what I mean down here. Okay, so let's start with a problem that you might remember from Calculus 1, taking the derivative of a product of two functions. How do we do that? Okay, well, you might remember the product rule sounds something like the first function times the derivative of the second plus the second function times the derivative of the first. Let's write that down. Okay, so the derivative of u times v would look like this. Okay, hopefully you can tell my u's from my v's here. Okay, so that's a true statement. And what we're going to do next is to observe that if that's a statement about derivatives, if we can take the derivative of u times v and get the function on the right, we should be able to turn the statement around and say that the antiderivative of the function on the right should be the function that we started with on the left. Okay, so if we take the antiderivative of the part on the right, we're going to get integrals of those two functions. And those integrals should take us right back to the function that we started with, u of x plus u of x times v of x. Okay, now we're being a little sloppy with the notation. Technically, there should be a plus c on the end of this. We're going to ignore that, though. It turns out that we don't need that for this formula that we're about to develop here. Okay. So one thing I'm going to do, just to simplify the notation first, though, is to rename some of these terms. So instead of writing u of x and v of x, let's abbreviate that by just writing uv. Okay, I'm going to clear a little bit of the clutter away here. Okay, so I'm going to call these two terms u and v. Okay, and then going to our integral, we'll do the same thing. So u of x and v of x, we'll write those as u and v. And then notice that v prime of x dx, that's the derivative of v with a dx tacked onto the end, so we can call that dv. And similarly, this u prime of x dx we can call du. Okay, so this formula then reads the integral of u dv plus the integral of v du equals uv. We're going to take that and do one more algebraic thing by taking this integral that I'm circling and just subtracting it over to the right-hand side of the equation. Okay, if we do that, we get a formula that looks like the integral of u dv equals uv minus the integral of v du. Okay, that formula is called the formula for integration by parts. Okay, we're going to do some examples that illustrate how this works. One comment I'll make, though, before we dive into our first example is that the integral that you see over here on the left, think of that as the starting integral, the integral that you're given. The general idea of this formula is we're hoping to take that starting integral and to simplify it somehow, to make it easier to do. Okay, so let's illustrate that process by looking at example 1 together here. They'd like us to integrate x cosine of x dx. Okay, now, again, if we sneak a peek at our kind of general integration formulas here, you will notice that x sine of x does not appear on this list. Okay, so we can't do the integral directly using our table of integral formulas, meaning we need to transform it into something easier. Okay, and so here's what we're going to do with this integral. I'm going to break it up into two pieces, x and cosine of x dx, and I'm going to choose to call that first piece u and the second piece dv, just to make it match this starting integral that we have here. All right, so let's write down those two choices that we made. U is equal to x, and dv is equal to cosine of x dx. Okay, I'm going to really try to write neatly enough so you can tell the difference between u's and v's. I know that's difficult. Okay, now, after we have chosen our u and our dv, we need to calculate the du and the v that go with them. Those are also pieces that occur in the integration by parts formula. So if u is equal to x, what would du be? Okay, well, du is just the derivative with a dx tacked onto the end, so the derivative of x is 1 times dx. Okay, and then what about the v? Well, the question we kind of have to ask is, if we start with dv equals cosine of x dx, how would we get the v? Remember that dv is like a derivative. Okay, so we really need to take an antiderivative of cosine of x to do that. Okay, whoops, sorry. So what would the antiderivative of cosine of x be? Well, if you think about it, that's just going to be sine of x, okay, because the derivative of sine is cosine. Okay, so there's kind of our work. And now what we're going to do is to actually write down the integration by parts formula. So we're starting with an integral that looks like u dv. The formula above tells us that that's equal to uv minus the integral of v du. Okay, so we'll write that down, and now we're just going to fill the pieces in. Looking over to the left, notice that u and v are x and sine of x, so the uv is going to become x sine of x, minus, and then we've got the integral of v is sine of x, and what is du? Well, that's just dx according to what we have over here. Okay, so we've got x sine of x minus the integral of sine of x dx. If we can calculate the integral of sine of x, we're done with the problem. Okay, so what is an antiderivative for sine of x? Well, it's negative cosine. Okay, and that's an indefinite integral, so we'll put a plus c on the end. And simplifying, that becomes x sine of x plus cosine of x plus c, and that is the answer to our problem. Okay, so we have done our first integral using integration by parts. Now, you probably have a lot of questions. This is unusual the first time you see it, and one question might be, how in the world did we know to choose the u and the dv the way that we did? That is an excellent question, and we will answer that. I'll give you some guidelines after we just do a couple of preliminary examples here, so stick with me on that.